Yeah, it's my pleasure to introduce Sucheta Majumdar, kind of, from Marseille. Yeah, she studied in India, IIT, Indian Institute of Science, Education and Research in Pune. And then she was postdoctoral researcher in Brussels and in France. And yeah, now she's in Marseille, and she will talk about kinematically algebras and their role in physics.
Thank you, Annegret. First of all, can you hear me well? I can try. Well, let me start by thanking the organizers for inviting me, for putting together this very nice conference, and also for making me a part of this community, the women in maths and physics. And I hope to learn, communicate, and make more connections within the communities. And yeah, thank you very much for making that happen. And we had a very nice discussion session just before this talk. We can connect more between ourselves, maths and physics. This is going to be largely a physics motive, but I'll still show you some maths, which perhaps will be of interest to many of you. And this topic is because it sort of sits cozily at the interface of maths and physics. And it is going to be about something called kinematical. Let me first say words. This is taken from an article by Dyson many years ago, and where he says that a kinematical Lie group is basically the group of invariances of a universe, which has certain nice properties like homogeneity and isotropy of space-time and so on. And we can translate these keywords into some more scientific terms, like by universe, we typically mean a kind of a class of space-times. An invariance group as in a group of symmetry transformations, and homogeneity and isotropy we typically relate with invariance under rotation and space-time translations. And the goal of this talk would be to actually tell you what these groups actually look like, and where can we encounter these kind of universes in different physical systems. Now, this is, for those of you who are well aware of this sort of programs, it's very similar to the client program that was mentioned, I think, by Sylvie or Alessandra, how we can actually think about space-times as being related to the group of symmetry transformations and what is being preserved, and from there we can study different classes of geometries and so on. And these kind of questions were already asked by some mathematical physicists back. I'm sorry, I got the year wrong. It's 68. In 1968, where they started with these key assumptions: invariance under rotation, space-time translations. They also added inertial transformations to it, which basically means invariance between two inertial frames. And then they studied this as a classification problem. What kind of Lie algebras do we get? And based on the assumptions that they were working with, they found that there are 8 such groups. For instance, De Sitter, Poincaré, Galilei group, and so on. And these are not completely unrelated. In fact, one can go from one to another through some group contraction. And the paper of Duval, Gibbons, and Horvathi back in 2014, where they showed that the asymptotic symmetry group of GR for asymptotically flat spacetimes, which is called BMS, is isomorphic to the conformal Carroll group. I will tell you exactly what the Carroll group is. I'm just trying to give you an overview of where this kind of topics can be useful. Now, mainly after these sort of analysis, the interest in kinematical Lie groups grew in our community. And in this talk, I will try to tell you a bit about these Carolian spacetimes and Carroll Lie algebras. And then, as I mentioned in this slide, if one is interested in building some sort of correspondence, then we also need to understand how to write down field theories on such Carolian manifolds or null hypersurfaces. So that is one reason why we can be interested in field theories on such manifolds. There are also other physical examples that I will tell you about at the very end of the talk. So perhaps that will motivate the physicists in the room to take these groups more seriously. And in writing down field theories, I would use the usual Hamiltonian techniques, because at least for now, I think this is where it can be done in a more clean and rigorous way. Of course, there are many other techniques people use to write down theories on Carolian manifolds. So, okay, as a disclaimer, let me tell you that I would keep switching between algebras and groups and like and null, these keywords, but whatever I say about the Lie algebras, this can also be done, these can be promoted to Lie groups, and that has been studied quite extensively. And I also want to make a disclaimer about the general relativists in the audience that, of course, these studies are not new, the black hole horizons or null hypersurfaces and so on. What I believe is new is the connection with group theoretic objects like these Lie algebras and how we can use the knowledge of those Lie algebras to make progress in the study of these kind of physical systems.
When you say kinematical, you just mean that it's not to do with the symmetries of the Hamiltonian or anything. It has to do with the symmetries of just the spatial hypersurface. I mean, is that why?
No.
Why are you calling it yeah, I didn't quite understand the use of the word kinematical.
No, it actually also tells you a lot about the dynamics. I think. I think it's really about. It tells you about the physical kinematics about the system. You can call them dynamical groups as well. I think it's something that I don't know. Maybe some of you have a better answer to that. I think it's something that physicists came up with. Yeah. But you will see that it captures all the isometries. When I define a geometry and I claim that this is related to that certain group, it is the group of all the isometries of that geometry. So it will also tell you about the symmetries of the Hamiltonian. So yeah, more precisely, these kinematical Lie algebras require a few key ingredients. So you'll need a SON subalgebra and two vectors like P and B. I call them P and B, but they don't have any. You don't necessarily have to think of them as momenta or boosts, but in physics, that is what they are. And there is another scalar with respect to the SON, and you may or may not have some central elements. And this kind of structure is called a kinematical Lie algebra, and the particular type of kinematical Lie algebra depends on the rest of the commutation relations. So these commutation relations basically define for you the basic kinematical Lie algebra structure. Now, when I say Galilei group, the Galilei group has this kind of commutation relation where the boosts commute, and the Hamiltonian with the boost give you the momenta. And the Bargmann group that I briefly mentioned before is actually the central extension of the Galilei group. So you can add a central element to this Lie algebra, and it looks like this. And then the Carroll group, which is the group of isometries of a null hypersurface, has these kind of commutation relations. Again, the boosts here commute. These two boosts will have different meanings in a physical system. I will show you in the next slide. And you can see that these two are very similar. So if I have a Bargmann group where this central element may be identified with the Hamiltonian of a Carroll group. So if you have, instead of one scalar, you have two scalars. And I can take one to be the Hamiltonian of the Galilei group and the other one to be the Hamiltonian of the Carroll group. So in this sense, the Bargmann group unifies Carroll and Galilei Lie algebras. And this is the basics premise of the kinematical Lie algebras that we are commonly interested in. But there have been many further extensions in different dimensions, in different cases, by relaxing some assumptions and so on.
Back to the slide in which, I guess, is Bakri and the blonde. Yes, the cube.
Yeah.
So here you have, so I understand the Galilean group and I understand Poincare and Sucheta. And you're going to tell us later why, so I mean, so what you're showing is different parameters which you can take you from one to the other.
Yeah.
But you've also got other pieces of this cube which you've said nothing about.
Yeah, because so if I have Galilei, I can take the static limit to S, sort of.
Okay, so these are just also other
Yeah,
groups of
yeah,
potential
yeah.
interests. And you're going to tell us why the static limit is interesting. I mean, as a physicist, I understand the first three groups.
Yeah,
I
yeah.
don't know what the Carolean group is.
Yeah,
What physical.
yes,
you're
that
gonna
is what
tell us.
I'm going to tell you about. And when they found these groups, they just listed them as a mathematical fun exercise that, okay, if you have these sort of assumptions, these are the possible algebras you can get. And later, people realized that this Carroll group also has physical relevance for different systems. And
Bargman group, it doesn't sit.
so yes, that's a good point. It doesn't sit in this box. It's outside the box, and I will give you the reason just in 1 sec. Or actually, you can. So here, when I take a group contraction, in a group contraction, the dimension of the group doesn't change. So if I have a 10-dimensional Poincare here, and I contract it to get Galilei or Carroll, I will get 10-dimensional, like 10-parameter Galilei or Carroll. But with the Bargman group, I'm saying it unifies it with one extra parameter. So it's like a Bargman in one higher dimension. When you reduce it in certain sense, like Kaluza-Klein are taking it as an embedding, then you get a lower dimensional Carroll and Galilei. So there are two different ways of getting these interesting groups. Kind of not, but I will tell you, for instance, the near horizon geometries that I think Sharmila had in her slides, they almost look like the Bargman space. You can define a Bargman space-time, and there is a sense in which one can define a Bargman structure with geometric objects that I will tell you in a minute. Yeah. Okay. As I said, I can even skip this part because I really want to tell you about the examples where these groups become interesting. So it's okay if you want to ask me questions, stop me anytime. We'll see how it goes.
I'm not sure what I'm saying, but I had understood that Sitter had a different signature than Poincare, than the Lorentz group.
Yeah, so for De Sitter, you have lambda non-zero. The cosmological constant or the curvature is non-trivial.
And this changes the signature?
No, for Lorentzian, you will, so I'm saying Poincare, which means Minkowski, which has zero cosmological constant. So the flat space limit can be framed either as
but the
lambda going to zero or curvature going to infinity.
Yes, but the underlying is Minkowski in Poincare.
Yeah, yeah.
In De Sitter also, I thought it
Sorry,
was...
the what?
In De Sitter, the underlying signature of the metric. I thought it was not the same.
No, it's not. It's not.
It's the same. Okay, so I'm wrong.
Yeah. Oh, I see. Okay, what you mean. Yeah. Yeah, exactly. Also, there is there are some fine prints in what I'm saying. That the De Sitter group is simple, the other ones are semi-simple, and that was the argument of Dyson actually. That how from that cube we could have predicted that our universe is De Sitter, and we could have predicted Hubble expansion just by some mathematical arguments, but we missed that opportunity. So that was the argument. Okay, so just to give you an idea of what the Carroll group is, when you look at Poincare transformations, so you're in a Lorentzian spacetime where we have a spacetime. Everything is relative. I can mix spatial and time-like coordinates. And the non-relativistic limit is more familiar to us because there we don't touch the time coordinate, and we only consider transformations in the spatial plane. And this is exactly what the the Galilei group of transformations is. On the other hand, you can consider a C goes to zero limit, and that will give you the opposite case where we only transform the time coordinates by this xi dependent terms, not the other way around. And the spatial part is sort of absolute. This is a bit counterintuitive because and in this light cone picture, if you think of it, if I take C goes to zero, the light cone is sort of collapsing on a light-like thing. And this is exactly what is happening. And this leads to a lot of singular and ultra-local behavior. So these theories are very counterintuitive. but these do appear in different physical systems. And so we do need to study them in great details. Again, defining the geometry becomes a bit unusual in some sense, but one can do this consistently. That's what I'm going to tell you about. Now, speaking of space-time, so here I was telling you about the group of transformations that one can consider. So what kind of space-times do we get? What does the metric look like, and does it have a special preferred direction or not? And let's say I have a Minkowski metric. So here, since c for us is like the speed of light, we have put back the factor of c here. Because if we want to take c goes to 0, usually we have the annoying habit of working in natural coordinates where we put everything to 1. So here, when I take the c goes to 0 limit, you see we get a degenerate metric. And we also have a special time direction, which is going to lie in the kernel of this metric. And this actually defines the Carroll structure for us. So we need some manifold, which is of d dimensions, and a metric, which is degenerate. And there is a special vector field, null vector field, which lies in the kernel of this G. And there are also stronger definitions with connections, so which tells you how to parallel transport on these surfaces. So there is a very nice geometric way to do this. And then the point is that the isometry of this structure is the Carroll algebra that I talked about. Now, if you're interested in writing field theories, then what we can do is we can take an Poincare invariant field theory, put back all the C's, and then take the C goes to 0 limit consistently. And this is what was done in this paper in the Hamiltonian formulation. I'll come back to the results of this paper here, but that's for the later part. Now, the key features, if you have a field theory and you do this, the key features that we find is that we get two kinds of theory from this C goes to 0 limit, because we have to scale the fields in a certain way in powers of C so that everything is finite and so on. And we can do it in two ways, such that the Hamiltonian only contains velocities, or the Hamiltonian only contains spatial derivatives. So the case where it only contains velocities is the sort of ultra-local case. And the magnet, we call it the electric Carroll sector, and the other one is called the magnetic Carroll sector, but those names are not important right now. And both of these are important to model different kinds of systems. Now, as I said before, it's a bit annoying to have to put back the C's everywhere, which we have set to 1 already. And secondly, we do know a lot of Lorentzian field theories, what the action looks like, what are the equations of motion. Is there a way to directly get that from the Lorentzian geometry? And that is related to the second method, which I call the null reduction method. So within a Lorentzian spacetime, we can consider two light-like directions, where both U and V are light-like here. No, actually, here, no. Just, let's say V is light-like. If you have two light-like directions, that's a special case. And you can write down a metric like that. And some familiar examples are like partial polarized, plane polarized waves, shock wave metric, and so on. And this kind of metrics or this kind of spacetimes also have something called the Bargmann structure, where one has a Lorentzian metric and a null vector. So this is a D plus one dimensional, let's say, manifold with a Lorentzian metric G, such that there is a null vector field. And this gives you a Bargmann structure. So basically, you have just taken a Lorentzian vector, Lorentzian spacetime, and picked out a preferred null direction. Yes, please.
Yes.
Exactly. Yeah. Yeah.
Sorry, not just any null vector.
Null killing vector. Yeah. Thanks for that. Yeah. And then, if you want to preserve that structure, the isometries are going to be the Bargmann algebra. And as I said before, algebraically, these two are related. The Bargmann group and can give rise to both Galilean and Carolian Lie algebras. And also geometrically, one can get both Galilean spacetimes and Carolian spacetimes by two different methods. So let me show you with the help of a picture. So if I have this kind of a metric and I have this null killing vector, we can also associate one form to this. And taking the quotient by n, this is just like taking a Kaluza-Klein reduction, but in a null direction along a null killing vector. We get this Galilean spacetime, and the key feature here is that you can define the inverse metric that is well defined, but not the metric. And one has this clock one form as a preferred direction. In the other case, we restrict to constant U surfaces. So this is like taking a null surface and embedding it in this Lorentzian spacetime. And here the key feature is that you have a degenerate metric, so you cannot invert it, and there is a null null vector field, which is special. Yeah.
Here's something where along the time direction, everything is degenerate.
Yeah.
So there's basically, in that sense, it is, what did you call it? Ultrastatic.
Ultra local.
Ultra
Yeah.
local.
Yeah.
So
sorry.
you don't, yeah, okay. So you will tell us more about that.
Yeah, exactly. And you're absolutely right, because you see this lies in the kernel of, this is the degenerate direction of the metric, of the Carroll metric. Now, I will take a special case where I can write down everything rigorously. Just for the purpose of this talk, I'll focus on flat Bargmann geometries and show you how to get flat Carroll and flat Galilean from that, and also maybe give you an example of a field theory, how a Lorentzian field theory can reduce to a Carolian field theory. Now, to do that, we take these light cone coordinates that we typically use in quantum field theory as well, as just planar null coordinates, x plus and x minus in d+1 Minkowski spacetime. And before I go into the details, let me very quickly tell you why, in general, these kind of null frames are interesting in quantum field theory. This goes back to the work of Dirac from 1949, where he says that for relativistic systems, there is not one choice of the Hamiltonian or time or the direction of time evolution, but there are three distinct choices. One is this light cone direction, the so-called Fermi form. So instead of the usual t equals x naught, if you take t as the null time coordinate, you get null foliations of this Minkowski spacetime. And this is interesting for several reasons, because the stability group of this surface is larger than the stability group of a space-like hypersurface at x plus equals 0. And in GR as well, these correspond to different initial value problems. This one is the Cauchy problem, and this one is related to the characteristic initial value problem. And also for recent interest in asymptotic infinity and trying to understand what is going on at the intersection at spatial infinity, it's interesting to look at these double null approaches, because it sort of mimics a situation where two null surfaces are intersecting at a codimension 2 space-like surface. And as I said, this is also, we can get a special case of flat Bargmann manifolds using these coordinates. And the reason is that in this coordinate, since we chose two null directions, we have these two vector fields, which are also killing. And if you look at the flat Minkowski metric in these coordinate system, it just looks like that. So we got rid of all the extra terms we had in the Bargmann, general Bargmann metric. And of course, the isometry of this structure is just Poincaré. There's nothing surprising there. And we can, in a field theory, we can write down the generator for these isometries. If you know what is P mu and M mu nu in terms of the fields, we can look at the algebra and so on. Now, what if we also wanted to preserve one of these null directions? And since we have two, we actually can preserve either one. And this way we get two different Bargmann structures. So, which means that within this 10-dimensional Poincaré group, let's say in 4D, we have two 7-dimensional Bargmann groups, which preserve this, the light cone metric, as well as one of the null directions. Now, just to give you an example of how this unifies Carroll and Galilei transformations, if I consider one of them, let's say B minus, you don't need to remember the details, what are these P plus, B minus, blah, blah. This B minus is the group of transformations which look like this. So X minus only mixes with itself. X plus can look like these, and Xi is spatial ones. If you do this embedding trick, if you restrict to a constant X minus, you get this sort of transformations, which tell you that space is absolute. So that's the Carroll case. If you take quotient by the n vector field, so if you get rid of these ones, you see that the Galilean time X minus is absolute, but the spatial directions are not. Now, as you can see, this is sort of an afterthought. I added this slide later, so these are handwritten drawings. But since I'm working in flat geometries, I thought it would be nice to actually draw some pictures where we can. So in this example, in the light cone Lorentzian example, let's say we chose the vector field to be del plus, then we can have a clock one form associated with this, which is x minus. And the point of this dx minus is that its kernel defines a good foliation. And if I restrict to one leaf of this foliation, then I get a Carroll manifold. And also this, we can, for those of you who work in GR, you may also be familiar with this rigging procedure for null hypersurfaces in black hole horizons and so on, which tells you how you can move slightly away from the null horizon, like near horizon geometries. This is also useful in the Carollian context because you have a one form associated with that as well, which you can pull back. And this gives you nice cuts on the Carollian manifold. So it will give you co-dimension 2 cuts. So this is basically the geometric picture that I'm trying to talk about. And all of this is also related to the Bargmann-Lie algebra, unifying Carroll-Lie algebra and Galilei-Lie algebra. So this connection was perhaps not that well appreciated 20 years ago, but now it has been, and it turns out that helps a lot with writing down field theories. Now, let me quickly show you one example of a very vanilla field theory. I'll take the Lorentzian scalar field theory and show you how we can get a Carollian scalar field theory. And I'll show you both the examples of this so-called electric and magnetic theories, and it will become clear why I said it's ultra-local and so on. Now, this is basically just the del mu phi Lagrangian, and this is invariant under the full Poincaré group, but we don't really need that. We only want to restrict to one of the Bargmann substructures. And to do that, we make a choice between the two null vectors. So I can choose either the m or the n. Let's say I choose this one. And that allows me to write a more general Lagrangian, because now I can add this term, and then it is invariant under the Bargmann group. I don't care about the full Poincaré. So this is invariant. This one is invariant under the 10 parameter Poincaré. Now this is invariant under 7 parameter Bargmann. And this also sort of means that I'm going from a light cone Minkowski spacetime to a more general flat Bargmann case. And this is sort of required to get both the electric and magnetic Carroll sectors, but that's a technical detail. Now, yeah, when I do this, then the other vector field does not lie in, sorry, this is not a right statement. It's not the preferred null vector anymore. This is not, it doesn't lie in the corner, sorry. Okay, now, as I said, I'm going to work in the Hamiltonian formulation. So we take this Lagrangian and look at the canonical momenta and the Hamiltonian density and so on. And we can write down a nice Hamiltonian action, which is invariant under the Bargmann group. And we also have this nice symplectic structure. Now, we can do the trick of restricting to a leaf of the foliation and so on, since we have all the geometric objects. But if I'm a field theorist and I want to take a Lagrangian and quickly, Lorentzian Lagrangian, and quickly get the Carollian field theory, we can also do a nice trick of just trying to evaluate the Lorentzian integral around a very narrow strip of this x minus equals constant. Then to do this, I'm going to insert this sort of a smearing function in the actional and assume some behavior of x minus behavior of the field. So I'm going to assume some behavior of the fields around this narrow strip. And the point would be that whatever I assume for x minus should preserve the canonical structure. And this is again related to the near horizon limit that was discussed in one of the talks, where I don't remember what exactly was being scaled, but there was a parameter epsilon, and I think the coordinates r is being scaled like this or whatever. So this is very much related to that procedure, because we are trying to, the gray area is near a null surface, but when I take epsilon to 0, it is the null surface. So and it's also easier to relate to the other method, c goes to 0, as a limiting procedure. So that's what we use. So once we have done everything rigorously, we get some Carroll action, which depends on these fields. either this one or this one, depends. So yeah, the way we choose the scaling is also very simple. We can not do anything and simply map the fields to the null hypersurface, or we can scale them inversely such that the canonical structure is preserved. And these gives us two different ways of getting Carolean field theories. So these are the two possibilities. So in one case, we don't scale with any factors of epsilon, the small narrow width. And in the other case, we scale them inversely. This here we get a Hamiltonian density. So this term, this is the kinetic term, this is the Hamiltonian density, which only depends on spatial gradient. So in this kind of Carolean theories, we see that the spatial derivatives become dominant, which more dominant than the time derivatives. And in the other case here, we see that the Hamiltonian only depends on the momenta, or in other words, the velocities. So that tells us that the time derivatives are more important. The time derivatives dominate. Now, you could ask me that, okay, these are some funny looking actions, but how do we know that these are actually Carolean field theories? Or in other words, if somebody gives me this action, how can we be sure that this is a Carolean action? And for that, we look at the hypersurface deformation algebra of these kind of surfaces. So we can look at deformations which are parallel to the surface and perpendicular to the surface, and these should be related to the Hamiltonian and energy momentum, Hamiltonian and momentum densities. And these are the deformation transformations away from the surface. And this was worked out nicely in the paper by Mark and Patricio, where they, can you hear me well? Where they listed down some necessary and sufficient conditions for any Hamiltonian action to be Carolean. So if you give me a Hamiltonian action, I can check whether this is actually Carolean or not. And the key feature here is, typically in quantum field theory, in Lorentzian quantum field theory, we find that the energy density at 2 points is not 0. It is related to the momentum density. But in this Carroll case, it is going to be 0. And this is true for both the electric and magnetic things. And this was already pointed out back in 1978. And this is why they are also called zero signature spacetimes. And the context I will tell you exactly what kind of physical systems this paper discussed, and in the first example that I'll give you. Now, and the other condition is very simple, that we check that the fields the Carolean action is invariant under these kind of transformation of the fields, which are generated by the hypersurface deformation. And we can also check how things transform under this so-called Carroll boost. So what we have established is that the two ways of deriving Carolean theories are equivalent, and we can prove in the physics way of proving things that these are exactly the same theories. And it works out very nicely for all sorts of bosonic cases. The fermionic part is a bit of slightly more involved, because we need to work out the Clifford algebras on these Carolean spacetimes. So we have to find gamma matrices which close on the Carroll metric. This is a work in progress, and we can also generalize this to curved geometries and so on. Now, in the last 7 minutes, I will give you some relevant examples. Now, the first example is the cosmological singularity that somebody mentioned in one of the discussions. That one has the BKL conjecture near the cosmological singularity, where the conjecture is that the evolution of geometry at different spatial points decouple when we are very close to the singularity. And this can be also framed as partial differential equations becoming ordinary differential equations. And exactly the time derivatives dominate. And there's a very nice image that I could not find. I tried till yesterday, so I could not find it. So instead, I would invite you to look at one of the standard textbooks. Maybe I didn't find the image in the textbooks either. So it's something very nice where you draw the singularity somewhere here and say these points are very close. I'm not drawing them close, but if you look at their light cones, they will meet at some point, but in this region, they are spatially decoupled. And the dynamics is just about how they are evolving in time. And this sort of near singularity dynamics is what the Bickel conjecture is about. And this can be modeled very nicely using Carolian field theories, because in electric Carol theory, this is exactly what happens, that the time derivatives dominate over space derivatives. And already Mark Hanno showed this in 1978, that the space-time near these singularities have this sort of hypersurface deformation algebra, not the Lorentzian kind. And then later, very recently, actually, it was also modeled using Carolian gravity. Okay, that is one interesting example. The other one is, of course, my favorite one, where we are interested in looking at gravity from asymptotically far away distance. And this is because the BMS group, the group of asymptotic diffeomorphism, the group of asymptotic killing vectors is isomorphic to the conformal Carol algebra. And here as well, there is a lot of other kind of physical questions one can try to understand using these tools. For instance, gravitational radiation and scattering processes. And in some recent works, it was shown that the soft modes of scattering is related to the electric Carol sort of behavior, and the hard modes of scattering, which happen very close to the interaction. So we can think of some interaction happening in the bulk of the space-time, something coming in and going out, and so on. And so the hard part of the scattering is very close to the interaction, and the soft part is what we see very far away, infrared behavior. And both of these can be modeled in electric Carol and magnetic Carol languages. And another example, which there have been some efforts to understand high energy scattering processes, particularly in QCD, using these kind of Carolian techniques. But some examples where it can be really useful is, for instance, some phases of quark-gluon plasma, where these kind of ultra-local behavior shows up. So if you consider two little blobs of quark-gluon plasma coming in, two little blobs of hadrons coming in together, they meet here, and then they give rise to quark-gluon plasma. Very close to this singularity. It's not all the phases are very well understood. Some are modeled by different classical fields, sometimes by hydrodynamics and so on. And of course, as you can see from the picture, this is a very null or near null interaction. So it would be very nice to see how much can be understood using these Carolian field theories. And in many other directions, these theories have been applied and some interesting results have come up. But in the interest of time, I'll just leave you with a list of, there are many open questions because this is a relatively new way of thinking about null geometries and so on. This is a biased list of things that I find interesting. So of course, a lot of things remains to be done. One important question that we really need to understand is how or whether we can quantize Carolian field theories, particularly the electric one, in a sensible way because of these ultra-local behaviors. So in the correlation functions, you may end up with squares of delta functions, which are not nice and so on. So that is a very big open question. And in this respect, I think the two ways of obtaining the same theory could be interesting, because oftentimes we see that even for quantum properties, if I have one way of like the C goes to zero limit, and on the other hand, if I have the null reduction procedure, do they lead to same quantum properties also? Classically, we can prove the equivalence. Are they also same quantum mechanically? And this is already in QFT a very interesting problem to show that equal time quantization is the same or not as the light front quantization. Secondly, there are many open questions about this asymptotic infinity and trying to model it using Carolian geometries, and phenomenology problems that I just mentioned, and a few other interesting problems. So I'll just stop there. Thank you very much.
Yeah, thank you. Are there any questions?
So this is connected to the intersecting null hypothesis. So if you look at it from the characteristic formulation, there are some constraint equations on the intersection. Oh,
Yeah.
right. So this is connected to the intersecting null hypothesis. If you look at it in any double null formulation, there are some constraint equations on the intersection.
Yep.
How do you see it in this formulation? Or maybe it's a question that's for the future?
No, actually, yeah, that's a very interesting point. It has been looked at in quantum field theory for certain things. So let's say you are working with just Minkowski. And for GR, I think there are some papers, I don't remember if I mentioned them. The characteristic initial value problem has been worked out, as you might know already. Yeah, these references are particularly nice, where they look at characteristic initial value problem at two intersecting null. I think that even before that, I guess the work, some works of Rendall and Kasia, I think as well, where they rigorously study the initial value problem. It has been looked at, but quantum field theory in curved geometries using double null, I don't think it has been done very extensively, to the best of my knowledge. Yeah, that is something. That's an open question for now, I guess.
Thank you for your talk. Underlying the more physical questions that you raised at the end, what are the mathematical questions?
Sorry?
What are mathematical questions underlying these physical questions you raise at the end of your talk?
Okay, interesting. Thank you very much. So let's jump to the end. Oh, okay. I also wanted to wish you a very happy New Year, which I forgot to do. All right. Let me give you some examples, like when you look at intersecting null hypersurfaces at the asymptotic infinity. These are also very interesting in terms of, so if I'm studying a physical interaction, so we have this Penrose diagram, things are coming in from here, something happens here, and then things go out. So we have to study how things are incoming and then outgoing and what is happening here. And there are different ways to zoom into spatial infinity. And in order to define these either initial value problem or time evolution properly, we have to do some parity conditions, take some parity conditions at this I naught point or antipodal map and so on. And in terms of mathematics, this has been studied very much in details with using the PDEs that govern these equations of motion and how to, I think in the discussion session as well, it was mentioned the Friedrich formulation of compactifying asymptotically flat spacetimes, where so we have a fairly good understanding of how to do CIVP here, also here, and here we are not so sure, but you can blow this up and then it becomes like a cylinder, and then you have to study the initial value problem here and connect it with these two. So that is a very deep mathematical, I don't know, I mean deep for a physicist, mathematical problem that people are studying already. Another thing, another interesting thing is about these radiative modes or soft theorems and so on. These are also often related to spontaneous symmetry breaking. So this BMS symmetry, there is it's sort of an open question whether this symmetry is broken because we typically see Poincare invariant observables. So what happens to the BMS group? Is it broken? And if it is broken, then how do we see this Goldstone modes and so on? So for that, what we really need to understand is how to define vacuum states and so on, which is related to the representation theory of these Lie algebras. And there are many people who are working on representation theory of Carroll Lie algebras and so on. So these are at least two examples off the top of my mind. That's why I said a lot of mathematical work still remains to be done because it's sort of a new way of thinking about these problems.
I don't quite understand, but how do why does the intersection of normally, you know, where C is not equal to going to 0, where does that, so where does the Carolian limit come in for intersecting null hypersurfaces?
Okay.
I don't quite understand.
No, in the intersecting case, it's not really like a limit. Both the intersecting surfaces are at. This is only on Sky Plus. And what I'm saying is, in GR, we have been studying Sky Plus as well for forever, but we typically use this kind of coordinate systems, one null, one radial. This is very nice because it gives you a lot of good structures at Sky Plus. But and what I'm talking about is doing this. And of course, each of these methods have their own drawbacks and advantages. One point here that I would like to mention is, this is already, at Sky Plus, for R going to infinity, this gives you a nice Carolean structure. But as you move away from Sky Plus, trying to go inside, the leaves of constant R are sort of like this. This is not really null everywhere. So the closer you are to spatial infinity, you don't really have this double null structure. But if you work with this, then you could think of them as double null foliation. So in some technical challenges, that becomes important. Yes, so this one becomes sort of Bargmanian. So you can phrase the problem as null and then slightly away from null by just going away in this direction. But if you do that in R, you're not null anymore. So large R and R equals infinity are two different things. But here, constant V means Carolean everywhere. So here the ruling is like this for UV, UV coordinate system. But for UR, it's like that. So you cannot use Carolean tools very much inside the bulk. But with this, you can. Yeah.
Yeah, so in the example slides, you mentioned about the soft modes and hard modes related to electric Carol and magnetic Carol. So I think the hard modes are those related to the black hole merger, like the gravitational wave modes emitted due to the merger of black holes. So like, why is it magnetic Carol? Maybe I missed.
Oh, okay. Now, this is actually just a nomenclature that comes from Maxwell's theory. So you don't really need to think of them as having some magnetic charge or electric charge. It's not really related to that. Maybe it's not a very good name. It came from there because initially these things were studied for Lorentzian to Galilean limit. And the idea was that the Lagrangian, Maxwell Lagrangian looks like E squared minus B squared. And depending on how you take the C goes to infinity limit, you either end up with E squared terms or B squared terms. And that's where the name came from. And E square, is related to F0I. So that's like the velocity. And P squared is related to Fij, so spatial gradient. But yeah, it's just a name.
Hello, thank you very much for the nice talk. I really much enjoyed it. I have a very stupid question, and that is, can you define this Carolean structure in every null surface, or you need some extra properties like expansion-free, twist-free, and shear-free?
Can you repeat the last part? I cannot hear.
Yes, so can you define this Carolean structure on any null surface, or you also need extra properties like expansion-free, shear-free, and twist-free?
Yeah, so exactly, that's a good point. What I discussed was just intrinsic Carol data, but if you are actually interested in physical systems, this is why I insisted on this Bergman way of doing things, because we rarely ever encounter null surfaces just on its own. It's always embedded in some larger manifold. Like you have a black hole horizon and we study near horizon structures and so on. So it's the way of going, also in this problem, when I say going inside the bulk, that is like, oh, I'm so sorry. Yeah, I'm so sorry. Yeah, let me just hold it like, yeah, so also this way of going away from the null surface, all of these are related to extrinsic data. And that is related to how you define expansion, shear, and so on. So I gave you a very vanilla example, but there are very nice reviews about how we can do this. And again, many of these things have been done in GR, but not in this language and not related to the Lie algebras and so on, I guess.
Yeah, sorry, but also on null infinity, right? Because for instance, if you have something that is not shear-free, then you would have some radiation in there.
Yeah.
So it is also on the hypersurface, right? So it is not clear to me, you also need these properties or it is completely general?
So the shear and everything is actually hidden in the form of the metric. So I said the Carroll structure is some manifold with a degenerate metric and a special null direction. So what you're talking about, the shear and expansion and so on, this is hidden in the behavior of this G, or you can think of this large R behavior. You have a G mu nu in the bulk and you expand it for asymptotically flat. Asymptotically flat basically means you have G mu nu, which goes like eta mu nu plus some 1 over R extra. And that extra is where the shear sits, right? So it is related to that.
Thank you.
Can I just also, so I didn't quite understand. So you had these actions. Are you then also translating that into a PDE, or how are you actually working with it?
Yeah, so if you think about initial value problems or those things, so these equations that I wrote here, just like in usual QFT or GR, equations of motions are what we use to evolve a set of data. So if I give you a data at x plus equals 0, how does it evolve at a later x plus? We can work that out using these equations of motion, and that reflects the geometry.
And so that has also all been checked, that it's well posed and local and global properties and so on. Do you know who has done this stuff?
I don't think it has been done to full generality, or because we are just starting to write down these kind of theories. But for Caroline gravity, some the group in Edinburgh, like Yele Hatang and Oling, they have quite a bit of work on this Caroline geometries, including torsion, without torsion, this and that, different ways of defining it. But I am not sure if they also study the initial value problem in great detail. But it can be done in principle. In some cases, yeah.
Okay, if there are no more questions, let's thank her again.
Thank you very much.